All right, let's get into it. Today, we're putting on our detective hats and digging into a patient's health data. Our mission is to see if we can use a handful of clues, things like glucose levels, age, and BMI, to predict one of the biggest health risks out there, diabetes.
So picture this. You've got a patient's file with just 8 standard health metrics. The usual stuff: age, BMI, blood pressure. The big question is, can we look at just those numbers and get a real sense of their risk for developing diabetes? That's the challenge we're going to tackle.
Yep, you heard that right. We're treating this whole thing like a detective story. The data, that's our crime scene. The health metrics, those are our clues. And our job is to figure out which of these clues are the real prime suspects, the key factors that point directly to diabetes.
Every good investigation has to start somewhere, and for us, that's the case file. In this case, we're working with a real-world dataset, packed with health records from a specific group of patients. So let's open it up and see what we're dealing with.
Okay, here they are, our 8 initial clues. We've got some pretty straightforward ones like age and BMI, right? Then we have some more clinical measurements like glucose and insulin levels. We even have this thing called the diabetes pedigree function, which is basically just a fancy score for genetic risk based on family history. But here's the real question. Are all of these clues equally important?
Now, just like in any real-life investigation, our evidence, well, it's not exactly perfect. We've run into a super common problem that data scientists deal with all the time: missing information. Some of the records are incomplete, and that, of course, is going to make our job a little bit trickier.
And wow, this number really shows you the scale of the problem. Almost half, 48.7% of all the patient records for insulin are just blank. That's a huge, gaping hole in a piece of evidence that we have a pretty strong hunch is going to be important.
So what does this mean for our investigation? Well, we think insulin could be a star witness, a really powerful clue. But when your key witness refuses to talk almost half the time, how much can you really rely on them? It makes insulin's role in all this really unstable, and we're going to have to be super careful with how we handle this piece of evidence.
All right, now for the fun part, the main investigation. It's time to sift through all our evidence, figure out which clues actually matter, and then rank our suspects from the most influential all the way down to the least. So how do we do that? Well, we have a system. First, we take all 8 of our clues, our features, and we run them through a bunch of different statistical tests. You can think of each test as a different way of interrogating the data. They each give us a score for how good a feature is at telling the difference between someone with diabetes and someone without. From there, we can build our rank list and really zero in on the most valuable leads.
Okay, the results are in, we've run the numbers, the scores are tallied, and the rankings are all set. It is time for the big reveal. Which of these 8 health metrics is really holding the key to this whole case?
And here we go. The first thing that just jumps right off the page is how consistent one clue is: glucose. Look at that. Across 3 completely different tests, it's number 1 every single time. Now check out insulin. Even with almost half its data missing, it's still ranking really high. That tells us it's powerful for sure, but that unreliability makes it tricky. Then we have BMI and age, which are consistently solid predictors, rounding out our top suspects.
I mean, the evidence is pretty overwhelming, right? While other factors definitely play a part, glucose concentration just stands head and shoulders above everything else. We've found our prime suspect. And honestly, it makes perfect medical sense. Diabetes is fundamentally a disease about regulating blood sugar, so it's totally logical that a direct measure of blood sugar would be the most telling clue of all.
So let's just break it all down. Our investigation is pointing to 3 really strong leads: glucose, age, and BMI. These are the clues we can count on. It's well known that higher age and BMI are risk factors that affect how our bodies handle sugar. On the flip side, things like blood pressure and that family history score, the diabetes pedigree function, they turn out to be pretty weak leads, at least on their own, in this data set.
And just to really drive the point home, the original analysis puts it perfectly. Glucose isn't just a strong clue, it is the, and I'm quoting here, strongest single variable discriminator of diabetes in this entire dataset. That is the absolute cornerstone of any predictive model we're going to build. Okay, so we've cracked the case. We've identified our most important clues. But what's next? The real point of an investigation like this isn't just about finding the answers. It's about turning what we've learned into a practical strategy that can actually be used in a real-world clinic. So here's the game plan.
A data scientist would start by building a simple, solid model using just our top 3 suspects: glucose, age, and BMI. Then, they'd very carefully try to fix that missing insulin data and see if adding it in actually makes the model better. Those weaker clues, yeah, they might get tested for small improvements, but the core strategy is built on our strongest evidence.
So, why do we even bother with all of this? Because this isn't just some academic puzzle. The real goal here is to move from a bunch of abstract data points to real, tangible improvements in how we take care of patients, helping doctors flag risks earlier and way more effectively.
And this right here is the ultimate goal, a clinical decision support tool. Think of it as a system that takes in those key patient metrics, our clues, and spits out a simple risk score. Now that score doesn't replace a doctor's expertise. It supports it. It helps them make a quick call on whether to order another test or maybe schedule a chat about lifestyle changes right then and there.
So what does success even look like for a tool like this? Well, a key metric is something called recall. And in plain English, that just measures how good the tool is at finding all the people who actually have the condition. A target of 80% means we want to catch at least 8 out of every 10 at-risk patients. And this is so important. It is far, far better to have a few false alarms than to miss even one single person who really needs help.
At the end of the day, the whole point of this data detective work is to build a system that can flag at-risk patients sooner. That allows for early intervention, which we know leads to better patient outcomes, and in the long run, it dramatically cuts down on the huge costs that come with managing late-stage disease.
So we did it. We've successfully ranked our suspects, and we found the most critical clues hidden away in the data. But the investigation, it isn't really over. The next, and you could argue most important challenge is this. How do we take these insights and build a seamless, reliable, and ethical tool that actually fits into the daily workflow of a busy clinic? A tool that genuinely helps doctors and patients make better decisions every single day. That's the question that really turns data science into life science.